Can I have an Oreo?
Did you push start?
Mm-hmm.
Okay.
Can I have an Oreo?
Yep.
Cool.
Could you close the door, please? Okay, if you could even see me right now, I'm going to post a picture. I am balancing the tripod on my head with the phone in it to film this because I can't do the other way. It's driving me crazy. So we're going to see how this goes. I have all the work done, and as long as I keep my page right here, it'll stay focused. The only problem is I can't see what's in here. I should get one of those dentist mirror things so I could like see and make sure that what's happening in here. Oh. Anyway, if this ends up messing up, I can't even do this video again. It takes forever. So here we go. This problem has parts A through, I think, O, which, yes, is ridiculous, but each part is actually really good. So here we go. I'm going to explain my work as we go. So they give me this picture. They tell me that this is f prime of x. This is valid on the interval -3 to 6. And it is known that f of 2 equals -3. So this is some random information that I'm not sure how it's used, but I put a square around it so I could look back. Okay, so first question is find f of -3. So we're kind of reviewing everything, but the first thing this is reviewing is talking about the integral as net change. How do we find out how much f changes by looking at the area under f prime? So if they want me to find f of -3, and I don't know anything other than what the graph of the derivative of f looks like, and I now know a starting spot, here's how I always approach these. If I want to know how much f has changed, I can find the integral of f prime from one x value to another, and that'll tell me how much change there was. So since I know what's happening at the x value of 2, and I need to know what's happening at the x value of -3, I'm going to just say, all right, well, at f of -2, I'm at -3, and I'm going to add on however much change there was from that x value to the x value that I'm looking for. When I look at AP's answers, they do it a little bit differently, but I like my way. It always works. It makes sense to me, so hopefully it'll make sense to you. But anyway, I don't know if you hear my kids cackling in the background. So to say that again, if I want to find f of -3, but I don't know anything other than a starting value and the derivative of f, I'm going to take that starting value and I'm going to add on however much change there was from that starting value to the x value I'm looking for. So f of 2 is -3, and then the integral of f prime from 2 to -3, so from 2 to -3. I calculated this area using a triangle. I calculated this area using a triangle formula. So I know that this area down here was 3, this area up here is 1. If I'm going from 2 to -3, I'm going backwards. So now the area below the x-axis is positive, did I go backwards wrong way? From 2 to -3. Shoot, did I go the wrong way? Oh my gosh, now my work is like sideways. From 2 to -3, this is below, so it's negative, but it should be positive. Crap, I thought I checked my answers. All right, hold on, I'm going to try, oh my gosh, to not move my head. We already have a problem. I checked my answers at a certain point, but I don't know if I checked there. Let me just check. I have the answers right here. Hold on one second. I would push pause, but like I mentioned, this tripod is balanced on my head. Oh my gosh, can you believe I messed up the first one? Oh wait, no I didn't. Haha. I didn't get down to it yet. Hold on. Do 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 do, sorry Charlie, do 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 do. You hear the one about the duck and the goose? No, me neither. Oh, the heron just flew by. I would move the camera so you could see it, but as I may have mentioned, I can't because the camera is currently balanced on my head. I'm just scrolling through the answers that they gave. So how's it going? Have you showered today? Good, good. Oh my God, who is it? This Wi-Fi has not worked right in my house since we got back. Haha, got back from break as if we went anywhere. The answer's right, then what the? -3. Oh my God, okay. Back to my work. This should be, and this should be the other way. Got it. Okay, my answer is still right. It's just that these are wrong. So the area from 2 to -1, since I'm going the opposite direction of normal, I'm going right to left. So the area below the x-axis is actually positive. So this is a +3. And then this area, which is actually above the x-axis, which would usually be positive, is now negative. So I have that. And now my work is correct. Okay, so there's part A. Hooray! I wish I had like confetti. Psh. Letter B. Evaluate the integral from 3 to -1 of 2 times f prime of x plus 5. Easy peasy, lemon squeezy. This is child's play. So I'm going to split this up. Anytime I have the integral of 2 things added together, I'm going to split them into 2, or at least I'm going to think about it that way. So I'm going to look at 2 times f prime of x. I'm going to pull the 2 out to the front. And I'm also going to look at the integral of 5 separately. So the integral of f prime from 3 to -1, I'm going back up to the picture. From 3 to -1, so I'm going backwards again. So now I think I do have it right. Here to here, this triangle has an area of 1. And this triangle has an area of 3. This part's going to be -1 because I'm going in the opposite direction. So area above the x-axis is negative. And the area of this is 3, but because I'm going from right to left, it's below the x-axis, so that area should be positive. Put that together and multiply by the 2 out front. That's going to be that part. Plus the integral of 5. So you can do this one of 2 ways, but the way I always think about it is, this is a function, y equals 5. That's a horizontal line up at 5. And I'm getting the area from 3 to -1. So from 3 to -1, I have a rectangle formed. That rectangle is just base times height. So 4 times 5, which is 20. But remember, I am going in the opposite direction. I'm going 3 to -1. I'm going backwards. So that area of 20 should be -20 because I'm going the opposite direction. Put them together, get -16. Okay, part C. Evaluate this integral of the second derivative. So we understand that the integral of the second derivative would give me the first derivative, but I have more than just the second derivative of f. I have the second derivative of f of 4 minus 3x. So I actually need substitution for this. I'm going to pick u to be the innermost thing, 4 minus 3x. So therefore du is just -3 dx. So I need to put that -3 into the problem and make up for it with a -1/3. And then rewrite the problem. -1/3 times the integral of f double prime of u. I also am going to rewrite my limits of integration. So we've done this a few times now since we've started reviewing. Plug my 1 in for x. Plug this 1 in for x. And get 4 minus 3, which is 1. Plug 2 in for x. And get 4 minus 6, which is -2. And now that's my new limit of integration. So now I have a brand new problem, all in terms of u's, and my limits have been changed, so I don't ever have to go back to the x values. I'm finished with that. So now the integral of the second derivative is the first derivative. So sweet. I've got the -1/3 out front, and I'm going to evaluate this from 1 to -2. So I'm going to plug -2 in. I'm going to plug 1 in and subtract. And these values come, whoa, that was like my voice cracked. These values come straight from the graph itself. What's the first derivative at -2? Well, this is a graph of the derivative. So the derivative at -2 is 1, and the derivative of 1 is -2. All those values just came straight from the graph. These make 3, multiply by that, you get -1. Okay, there's C. Part D. It is known that the integral from -1 to 9 of 1/2 times f prime is -3. Find the integral from 9 to 6. So first realize that when I'm talking about the integral of f prime, I know a lot of stuff from -3 to 6, but I don't know anything after 6. I have no clue what happens. So they want you to find the integral from 9 to 6. I'm going to work on finding the integral from 6 to 9, and then I'll just flip my sign. But I'm trying to figure out what happens over here. So first I need to figure out, well, what's the integral from -1 to 9? What's the integral all the way from -1 to 9? Because then I can take out whatever the integral is from 1 to 6, because I know that, and be left with the integral from 6 to 9. So I start with this, and they're just being jerks by putting a 1/2 in here. So I took the 1/2 to the front, and then I multiplied both sides by 2, just so I could have what the integral is of f prime from -1 to 9. So from -1 to 9, my integral is -6. So I ignored that. I ignored the next part for a second and said, okay, the integral from -1 to 9 is -6. So I drew like a little picture. And I was just thinking, okay, from -1 all the way to 9, the area is -6. So like I had this total amount of area. It's not all under the x-axis, but when I put it all together, it has like this cumulative value of -6. So then I went and said, well, what is the area from -1 to 6? Because I know that. I can do that myself with the graph up above. So that's what I went here. I said, from the picture, we know that the integral from -1 to 6 of the derivative is this. So I went to the picture and I said, okay, from -1 to 6, -1 to 2, I have an area of 3 below the x-axis, and 2 to 6, I have an area of 4 above the x-axis. So my area from -1 to 6 is -3 plus the 4 makes a total of 1. So then I went back to my picture and I was like, all right, if from -1 to 9, we have a total of -6, but from -1 to 6, we have a total of 1, how much must we have from 6 to 9? So I don't know if that makes sense in your brain, but that's how I think about it. So I think if this much is -6, but here to here was 1, how much must 6 to 9 have been to make the entire total -6? So I figured that the area from 6 to 9 must be -7 to make all of that work. So if the area from 6 to 9 is -7, they want the area from 9 to 6, so from 9 to 6, the answer would be +7. There's part D. Don't worry, just E, F, G, H, I, J, K, whatever the alphabet is to O left. Oh boy, oh boy. Hey, Elias! Can you come check this? Sorry, sticky note. I want to make sure I didn't. Can you make sure you can still see it?
Yes, ma'am. Yeah, you're good.
Thank you. Okay, so now we're going to go into some max and min problems. And these always just lead me back to like, I'm going to kill him. To what do we know about maxes and mins? So I tried to kind of write down for each problem what you know about maxes and mins. And like I keep saying in these videos, if you just stay in your lane and you focus on what you know to be true, you can apply it to these crazy problems. And that's what they want you to do. Take what you know to be true and apply it to this just like, question that's kind of worded in a weird way, or the whatever, blah, blah. Okay, party. So they just repeated the problem up here. Find all x values from -3 to 6 where f has a critical point. For each x value, determine whether f has a min, a max, or neither. Give a reason for your answer. So first of all, how do we know what a critical point is? Well, f has a critical point whenever the derivative is 0 or the derivative is undefined. This is a graph of the derivative. Where is the derivative 0 or undefined? So the derivative is 0 at the endpoint, at -1, and at 2, and at the endpoint. So they gave me an open interval here, so I don't have to worry about the endpoints. So there's a critical point at -1 and 2. That's it. This derivative is not undefined anywhere. The derivative of this graph is undefined at the corners, the 3 corners. But that would mean f double prime is undefined. F prime itself, This is a picture of it. It's not undefined anywhere. If it was, you would see an asymptote or a hole, but you don't see that. So this is defined everywhere. The critical points are only at -1 and 2. Now, which ones are maxes, which ones are mins? So I wrote on this little sticky note just to help you remember what, this would be good to like pause and write down. This is a little recap on how f prime relates to f. So when f prime is positive, a function is increasing. When the derivative is negative, a function is decreasing. So when the derivative changes from positive to negative, f is going to have a max. When the derivative changes from negative to positive, f is going to have a min. I'll bring that note back in a second. But so what's happening at -1? This is a graph of the derivative. The derivative is changing from positive to negative. So therefore, I have a max at that point. And at 2, the derivative is changing from negative to positive, so I have a min at that point. Okay, part F, find the maximum value of f of x on the closed interval -3 to 6. So maximum values mean like find the absolute max, and they're giving you endpoints. So absolute maxes happen at either the critical values or the endpoints. These are the ones where we need to get the critical values and get the endpoints and check them. Test them, plug them into the original to find the y values. Excuse me. Allergies. The smallest y value will be your min, your minimum value, and your biggest y value will be your maximum value. So I need to test the endpoints, -1 and 6, and I need to test critical values. Now I didn't pick, here's it's -3 and 6 are the endpoint, sorry. -1 is the critical value. I didn't pick both critical values because 2 is a min, and I'm asking for the maximum value. So I don't even have to worry about that one because I have a min there. So I need to find out what is f of -1, f of -3, and f of 6. What are the y values that go with those x values? So I came over here, f of -1, f of -3, f of 6. So again, try to like stay in your lane. Refer back to part A when they asked us, let's start with f of -3. We found this already in part A, and that does happen with these problems where you can go backwards and use information that you already found. So f of -3 we already found was -1. Do you remember how we found it? If not, go review that part because we're going to use the same method to find f of -1. F of -1 is found by taking, pardon me, the place that we know and then integrating from the place that we know to the place we're trying to find, for integrating the derivative. So I'm taking f of 2, which I know, and I'm adding on the change from that x value to the x value that I'm looking for. So I'm taking the integral of the derivative from that point to that point. This is where I know, this is where I'm trying to go. Haha, that rhymes. So when I put this together, I go up to the graph again, and I'm going to integrate from 2 to -1. From 2 to -1, I had an area of 3. The area is below the x-axis, so it's negative, but I'm moving backwards, so the area is actually positive. So f of 2 is the starting amount plus the amount of change gives me a value of 0. That's the y value for that x. I'm going to reach and grab my tea because I keep coughing. Okay, and then f of 6, again, I'm going to take the starting value and I'm going to integrate the derivative from 2 to 6. So 2 to 6 had an area of 4. We're moving in the left to right direction, so area above the axis is positive. Starting value plus the amount of change equals the total of 1. So here are my y values. I'm looking for the max. This is where my maximum value happens. They didn't say find the x value. They said find the maximum value. That would be just the y value. The biggest y is 1. Okay, part G, here we go. Find any open intervals where the graph of f is both decreasing and concave down. Refer back to this little sticky note again. We looked briefly at the way the derivative relates to the original in terms of increasing and decreasing, but how does the derivative relate to the original in terms of concavity? So when the original function is, when the derivative of a function is increasing, f will be concave up. And when a derivative of a function is decreasing, f will be concave down. This is hard to get into our heads because we're so used to like thinking about original functions being increasing and decreasing. But now we're looking at it a little bit differently. Where is our derivative increasing? Literally means going up, because that's going to be where f is concave up. And where is our derivative decreasing? Going down, because that's going to be where f is concave down. So find any intervals where f is both decreasing and concave down. Well, that's going to happen when f is decreasing when f prime is negative. So that's going to be in this section here. But then f is concave down when f prime is decreasing. This is f prime, it's decreasing here. So only in this chunk from -1 to 1. I just realized they said find the open intervals, so these should be open parentheses, but they're never going to take points off for that. They don't care. Okay, part H, order the values f of 2, f prime of 2, and f double prime of 2 from least to greatest. So we've done these kind of problems a million times with multiple choice. Now they just want you to put them in order yourself. So we need to know what is f of 2, what's f prime of 2, and what's f double prime of 2. F of 2 was given, it was -3. F prime, that's right in the beginning, right? And it's up here. F prime of 2, this is a graph of the derivative. So what's the value of the derivative when x is 2? So the value is 0, the y value is 0. And then what's the second derivative of 2? Well, if this is the first derivative's graph, the second derivative is the slope of this graph, the derivative of the derivative. So when x is 2, what's the derivative? What's the slope? Well, we have a line here that has a slope up 2 over 1. So the slope of this line is 2. So that's the value of the second derivative. So I can put these in order, smallest, middle, biggest. All right, let's see if I can do this without moving papers. Okay, we're still with the same kind of question, and then we move on to something different. Find where there's a point of inflection. Again, you can refer back to this pink sheet. There are points of inflection when concavity changes, right? So there's points of inflection when the derivative changes from increasing to decreasing or decreasing to increasing. Well, what does that look like on a derivative graph? That looks like a max or a min. So when a derivative has a max or a min, f will have a point of inflection. So where does f have a point of inflection? And give a reason for your answer. Whenever the derivative changes from increasing to decreasing or vice versa. So that's going to happen at x equals -2, x equals 1, and x equals 3. My reasoning could also have been whenever f prime has a max or a min. But this is probably the better explanation. Okay, part J, we're getting there. Find the average value. So do you remember there's a formula for average value? We did it during class, but I put it here. So there's a formula for average value. This was the kind of thing where we said, like, you have some function on some interval, there exists a y value such that if that y value created a rectangle out of that same interval, the area that was left up here would fit perfectly into the space created by that rectangle. That particular height that you're finding is what we call the average value. You do need to know that concept, but also for this problem you don't. For this problem you only need to know the formula. So average value is finding the integral from a to b, so left x to right x, of the function times 1 over the b minus a. So this is really just a formulaic problem. I want to integrate from -3 to 6. I want to multiply by 1 over 6 minus -3 of f prime. My kids are singing Backstreet Boys while playing Y2K in there. I can't even. So anyway, here we go. Blah, blah, blah. That makes 1/9. And then what's the integral from -3 to 6? So -3 to 6, we've used these areas a million times. I don't even have them on this paper, but I think this area was 1. Yep, this area was 3, and this area was 4. So we've got 1, and then -3 because it's below the x-axis, and 4. Put all that together, we get 2/9. Okay, part K. The average rate of change for f prime over the interval 1 to 6 is equal to 2/5. But there's no value of c in that open interval such that the second derivative is 2/5. Explain why this does not contradict the mean value theorem. So what they're saying here, before you even read my answer, is They're saying from 1 to 6. The average rate of change is equal to 2/5. Oh, 1 to 6. I was going to say -1. Okay, sorry. From 1 to 6. The average rate of change is 2/5, up to over 5, or in other words, the slope of the the slope of the secant line, the slope of the line that connects those two endpoints is 2/5. Explain, but there is no place on the second, there's no place that the derivative of this will equal 2/5. So, all right, back up. The mean value theorem says that when you connect the endpoints of a chunk of a graph, and if you get the slope between those two endpoints, somewhere in between, the derivative must equal that same value of the slope that you found between the two endpoints. So there should be a place along this graph where the slope is 2/5. But this is saying that doesn't happen here. Why not? Well, the reason why not is because this graph is not differentiable at 3. There's a corner there. For the mean value theorem to apply, your graph must be continuous and differentiable for all values on the interval. This isn't. So let's say instead this was a curve of some sort. Well, then it would work. The slope would be 2/5 between the endpoints, and then maybe about here, the slope would be 2/5 again. That's the mean value theorem, that the slope between the two endpoints equals the slope somewhere else, the instantaneous slope or the derivative. But if you have a corner or cusp like that, that's not going to be guaranteed. In this case, definitely doesn't work. So the reason why, explain why this does not contradict the mean value theorem is because the mean value theorem doesn't even apply. This has a corner, so the mean value theorem does not apply. Oh my gosh, LMN. Okay, now things got really real and the work got really gnarly. So maybe pause, go get a nice tea, come back. Part M in particular. I wonder how long this video is. I can't even see it right now. So let's start with L. Try to ignore what's down here. I don't want to put a paper on because I don't want to mess it up. So L is an Euler's method, which should be really easy, but they put a hitch that made it, I had to go look it up because I wasn't sure what to do. So this is an Euler's method. So if you remember, I showed that in a video, I think on Monday. So Euler's method has us doing this thing with the step size and stuff. And to do Euler's method, they're going to have to give us a derivative, which they do. They're going to have to give us an initial spot, and they have to tell us where we're headed. So this says, starting at x equals 2, approximate the value of g of 0 using Euler's method, and knowing that our starting x has a y value of -3, and that this is the derivative. So to do this problem, there's like a systematic approach. We start out with saying, okay, what's the first x they give us? What's the first y they give us? And then let's go calculate the derivative at that spot. Well, this is where things got weird and I wasn't sure what to do. I think I understand. I thought to find y prime, we would just plug our numbers, x and y, right into this derivative. But I was a little bit wrong, I guess, when I looked at the answers. dy dx, I don't really totally understand. They took this and they solved this for dy. So they said dy was this whole thing times dx. And what I figured, the thing that I was missing is they said that dx was -1. So dx stands for the change in x. And I guess because we're starting at an x value of 2 and ending up less than that, usually Euler's method has us increase in size along the x. But because we decreased by 1 each time, they said that the change in x was -1. So they said that dx was -1. I've never seen that before, so I don't know if it's going to show up on the test like that or whatever, but I don't know. You learn something new every day, right? So my derivative that I used was the derivative they gave me, but times dx, which we are going to say is -1 because the x is changing -1 from one to the other. So back to Euler's method. Starting x, starting y, get my derivative using the derivative formula that they give me. So plug in -3 for y, plug in 2 for x. Everything else is in the formula. Reduce. Find f prime of 1, which is in my graph. F prime of 1 is right here, -2. This is the graph of f prime. Put it all together, I get -3. Move on to the next line. So the next line is, I'm trying to get down to 0. My step size is 1. So my next x is x equals 1 away from this. What's my next y? So this is where Euler's method comes in terms of what you're supposed to know. So Euler's method says to find the next y, you take the slope from the step that came before times the step size plus the y value that came before. I wonder if we could have fixed our problem. Like, I wonder if I could have just used dy dx, I would have gotten a +3 without worrying about this thing. And then had my step size be -1. You know what? I totally could have. That's how I would think about it instead. Ha ha, you little suckers. So you know what? I would not worry about this. Take what I said about that and throw it away. Take out this -1. I'll go fix my answers for when I post this, the picture. And therefore this is 3. So plug in, when I'm using Euler's method, then I'm going to have the slope from the problem the slope from the step that came before times the step size. I'm going to make my step size -1 because that is my step size. My step size isn't 1, it's -1. And then add on the y value that came before. So I'm still going to get -6. Yep, that's what I would do. Yay. Okay, so now I have the next x, the next y, and I need to find the next derivative. So use the derivative formula, plug in the y I just found, plug in the x from that step. Don't worry about this -1. I'm going to get 3 again. So now my next step, I have my next x value, and my next y value is using Euler's method. The slope that came before, which is now +3, times the step size, which we're saying is -1, plus the y value that came before. And there's my final answer, -9. So that's Euler's method. If you didn't watch the video from Monday, go watch it. It's not hard. You just have to kind of practice a couple times and you'll be fine. Okay, letter M, Maclaurin series. What? So we haven't even reviewed series yet. I don't know that we're really going to specifically review it, other than we're going to take it when it comes. I think that, I don't know, hopefully the College Board's going to do a little series review thing, but I'm not sure. It's probably just going to come up in our practice. So you can see from all of this work, there was a lot of work, but it was all makes sense. I just really took it slowly so I didn't get myself lost. So to do a Maclaurin series, I don't even know if you remember how to. Go back, look it up. Writing a Maclaurin series, to see if I can write up here. If you remember at all, it's really systematic. We take the value of whatever function we're trying to find a Maclaurin series for. We take the value of the function of 0. We add on the first derivative of the function at 0 times x. Then we add on the second derivative of the function times x squared over 2 factorial. Then the third derivative of the function at 0 times x to the third over 3 factorial, and so on and so on. So as long as we understand how to write one, we can always follow those steps. The rest of it's easy. Except in this case, there was a lot of calculation. But that's how you write a Maclaurin series. Go back, look it up to remember. So to write a Maclaurin series, what I need all of these guys. I need f of 0, f prime of 0, f double prime of 0. So this is where they're being just total jerks. They're telling me what h of x is. That's it. And I have to write this second degree. Second degree means go until your power of x is 2. So I'd be going like this term, and this term. I don't need to worry about that one. So I have h. I need h prime, and I'm going to need h double prime, because I'm going to need to find out what h of 0 is, h prime of 0, and h double prime of 0. I need a numeric value. So if h of x is this, I need to find the derivative. So I'm going to find the derivative now. So the derivative of 2x is 2. The derivative of 3 is 0. And then the derivative of this integral. This is Leibniz law. Leibniz law is used when I take the derivative of an integral. It's a shortcut to do that. So Leibniz law says take the upper limit, plug it in for the variable, and then multiply your expression by the derivative of the upper limit. So take e to the 2x, plug it in for t, leave that alone just how it is, and then multiply by the derivative of the upper limit. The derivative of e to the 2x is e to the 2x times 2. So this is the first derivative. I cleaned it up a bit. I put this in front of this term. But this is the first derivative of h. It's annoying, but there's nothing here that you can't do. Just be careful and be slow and, and neat so you can see your work. If you try to fly through it, forget it, you're going to get lost. Now I also need the second derivative of h. So I need to take the derivative of this. The derivative of 2 is 0, but the derivative of this needs product rule. I'm going to have this term times this term. So here I have the first term times the derivative of the second. So this is a chain rule problem. The derivative of this is going to be the derivative of f with respect to what's inside times the derivative of what's inside, plus the second term times the derivative of the first. So this is a huge product rule problem. Now I took my work over here. I have h prime, and h double prime. Now I need to plug 0 into all three of them. So I plugged 0 into h, and I got 0 plus 3 minus the integral from 1 to e to the 0. So what is that? E to the 0 is just 1. So it turns out that I got 0 plus 3 minus this integral, which is really just from 1 to 1. Well, the integral of anything from 1 to 1 is just 0. There was nothing to calculate. I thought it was going to be funky, and it wasn't. So it was just 3. Now I'm going to plug 0 into the derivative. So I have 2 minus, I'm kind of going between these two, but the first derivative of f of e to the 0 minus 1 times e to the 0 times 2. So I've got all that written out here. I reduced it all. This e to the 0 becomes a 1. This f prime of this becomes an f prime of 0 because e to the 0 is 1. 1 minus 1 is 0. I calculated this just using the graph. F prime of 0 is right here. It's negative 1. Put all this together and I get 4. This, if you're just watching and you're not actually doing the work, this is going to seem like, what the heck is happening? You got to go through and do that work yourself. The second derivative is 0. I'm plugging 0 into all of these x's. Follow my work. I tried to take it step by step so you could see where everything was coming from. So finally, h of 0 is 3, h prime is 4, h double prime is 8. I can write the series. H of 0 plus the derivative of h of 0 times x plus the second derivative of h of 0 times x squared over 2 factorial. There's the series. Like, that should be an entire problem, and it's part M of 1. I can't imagine this is a problem that you should do in 25 minutes. That, like, A through O, there's no way they're putting all that in 25 minutes. But all this stuff is good, man. All right, letter N. This is an integration by parts problem that's actually a little more complicated than what we have learned. It required you to do integration by parts twice and do some crazy algebraic manipulation. I'm going to skip it for now. I feel like it's not going to show up. Integration by parts will, but not where you have to do this repeated form. So we're going to say no thank you. Almost done. Part O. Write but do not evaluate an integral expression in terms of x to give the arc length. So arc length they're throwing at us again. So what I'm hoping with these videos is that things are going to start repeating for you. You're going to see them multiple times, and then that's when you start to remember. It's like preparing for the SATs. Like, you learn the math for the SATs over 3 years of high school, for algebra, geometry, and algebra 2. Then you go take the SATs, but to take them, you need to be familiar with the way they're going to word problems. That's what this is. We learned calculus for however many months, and now we get familiar with the way they're going to ask questions. So the more you see things over and over again, the more you remember, oh yeah, we just did that yesterday. So arc length has a formula. I put it on there yesterday. So the integral of the square root of 1 plus the derivative of f squared. This one only wants an expression. You don't have to evaluate it. So I actually got stuck on this for a second. I was like, all right, there, I know what the formula is, but what the heck is the derivative of f? Like, they only give me a picture. And then I was like, oh wait, from -2 to 1, -2 to 1 is just this part. Well, if it's just that part, I can actually come up with an equation for that part of the graph. I know that at this part, the derivative is, since this is the graph of the derivative, this function itself is just a line. It goes through a y-intercept of -1. It has a slope of -1. So this graph is just y equals -x minus 1. That's the equation of that line. If we went from -2 all the way over to 6 or something, then I'd have to like split this into parts, or I don't even know. But since they just gave me an interval with which I can find the formula for that part, that's all I got to do. So f prime can be written as this line. Now that's some kooky, like pulling something out of left field, but it's still pretty cool. So there's the average value. And last problem, last part of this problem, here's a graph, has nothing to do with anything else. It's a separate function, p of x. Is a left Riemann sum an over or an underestimate? Give a reason. So whenever we want to know if something is an over or underestimate with the Riemann sums, we just want to know if our graph is increasing or if our graph is decreasing. Because if our graph is increasing, left sum will be an underestimate. If our graph is decreasing, our left sum will be a blah, 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 overestimate. So I just draw the picture to know like whether I'm going to have an over or an underestimate. So all I really need to know is p of x increasing or decreasing? So I'm going to find out, how do I find out if something is increasing or decreasing? I look at its derivative. So if this is p, I'm going to look at what's the derivative of p. So what's p prime? Well, the derivative of e to the negative f of x is e to the negative f of x times the derivative of the power. The derivative of negative f of x is negative f prime of x. There's my kid at the window, which I would show you, but I can't move. So I just need to figure out, is this derivative positive or negative? Well, e to a power, no matter what that power is, this will always be positive. If that power is negative or positive or a fraction, it doesn't matter. This letter, or this number e, any positive number really raised to a power, will always be positive. Could be small, it could be a fraction, but it'll always be positive. This is saying, okay, this is f prime of x. It's actually the negative f prime of x. What will this be? Well, since I'm on the interval from 2 to 6, I went and looked up here from 2 to 6. F prime is always positive, always above the x-axis. So what's negative f prime of x? Well, negative f prime of x must always be negative. Since f prime of x is always positive, negative f of x is always going to be negative. And a positive times a negative will be negative. So therefore, the derivative of p is going to be negative. Therefore, p is going to be decreasing. So a left sum of a decreasing function is going to be an overestimate. Oh my God, I'm taking this off of my head. That was ridiculous. Oh, low battery, 43 minutes. I really, really hope it worked. Oh my God, I have a headache. My neck hurts. Ow. See, this is what I'm sacrificing. So get on, figure this stuff out, see what you have questions on, get in the game. Oh my gosh. And have a great day. There's one more problem to do. I don't even know how many parts it has. A, B, C, D, E. It has through H. I'm going to have to take a break before I do that one. Have a good day.